Well, first of all, I'd like to thank Nasa for inviting me to give a talk. And yeah, what I want to talk about is Pfaffians in relation to non-commutative integral systems. So I'm not sure. So I want to tell you a few different things, and this is work in progress because there's lots of kind of interesting features to this work. So let's, oops. So, okay, so I'm going to start by just saying a little tiny bit about the non-commutative KP equation, partly because that's my favorite equation. And then I know you've had some talks last week on quasi-determinants, so I will tell you some of the basic things that are useful for this talk, but I won't say too much about quasi-determinants. I'll then tell you about Pfaffians, because people are less familiar with Pfaffians than they are with determinants and Wronskians and such like. So I'm going to tell you a bit about Pfaffians and Pfaffian identities. The reason I'm doing this is because I want to then look at something I call quasi-Pfaffian, which is the sort of non-commutative version of a Pfaffian. These are very interesting. I have my definition. I know other people have some other different ideas about definitions. Shihao Li has a slightly different definition, but the basic essence of it is in what I'm going to tell you today. And then hopefully we'll look at some equations and some ways towards its solutions. There's a lot of questions that still need to be answered for this, but there's a lot of interesting things that have been answered. So first of all, just a little bit about the KP equation, just to introduce non-commutativity. So this is maybe one of the most well-known non-commutative integrable equations, and the non-commutativity comes in a really quite simple form here, because this is at the top we've got the KP equation, and then below is the non-commutative KP equation. Well, it's convenient to write it in this form because I don't want integrals in my equation. So the V relates to the U in the KP equation by just Vx equals U. So the only difference between the KP and the non-commutative version is this extra term sitting on the end, the commutator of Vx and Vy. And if we allow things to commute, obviously the Vx and Vy commutator vanishes, and we get back to exactly the KP equation. Like normal commutative equations, it's got an associated lax pair, and here it is sitting down the bottom. So it's not really significantly different from the KP, except we just keep the order of everything. Okay. Right, so let's say a little bit about quasi-determinants. So if we take a block matrix, and so this matrix has a square block in the top A, then a column B, a row C, and a single entry D. And if I look at this matrix, and let's say A is an n by n matrix, and B and C are their own column vectors. If I put a box round the D, and I call this my quasi-determinant expanding about the bottom entry D. And so this quasi-determinant is, I can define it very simply. It's basically D minus C times A to the minus 1 B. So it's, people often define this iteratively, but this, if you don't want to define it iteratively, you just make this your definition. Okay, so, but indeed, if you do things, you realize that this object here, the D minus C a to the minus 1b, is really nothing but if you take the inverse matrix and you take the bottom corner entry, that is just the inverse of the quasi-determinant. So quasi-determinants are very much related to matrix inverses. Okay. Right, so if our entries in our matrix commute, if everything commutes, then your quasi-determinant actually turns out to be the ratio of one determinant divided by the determinant where you've removed the outside row and column, bottom row and the last column. So this is what happens in the commutative case. Okay, so we have identities. This is a determinant rather than a quasi-determinant, and you've got a Jacobi's identity. So this is an identity that you'll probably be familiar with. Excuse me. It basically says that take a determinant, multiply it by a determinant where you've removed 2 rows and 2 columns. That itself is the determinant of with 4 entries where each entry has 1 row and 1 column removed. So it looks something like this. Well, quasi-determinants have similar sort of identities. Let's have a. So this is the quasi-determinant equivalent. So this is usually called Sylvester's identity. And here we've got a quasi-determinant with matrix A here, and then 2 extra rows. This is a B1 and B2, and 2 extra columns, C1 and C2. Okay, so then you can rewrite that as the quasi-determinant of, much like the determinant case, you write it as the quasi-determinant of the smaller quasi-determinants, where in each one you just take 1 row and 1 column. So this is a nice identity. Notice it's a little different from the determinant identity in that the determinant identity is bilinear and occurs everywhere in sort of, if you're doing Herota's bilinear approach to things. This one isn't bilinear because over on one side we've got the quasi-determinant, the full quasi-determinant. On the other side we've got something that's bilinear. Well, in fact, it's not bilinear because it's got a single entry and then it's got an entry times an inverse times an entry. So it's not a bilinear object. Now, the important thing about quasi-determinants is that when you differentiate them, you get very simple things. And this is the whole key to why this is turns out to be very useful. And so let's look at the derivative. This is not really what I'm differentiating with respect to just for the moment. But if I differentiate a quasi-determinant, I get, first of all, the derivative of the D, and then I get, well, the quasi-determinant is C a to the minus 1b. So I get the derivative of C times a to the minus 1b. Then I get a term in the middle, which I've done a slightly different color. I've done blue. That's minus C a to the minus 1 differentiated b minus C a to the minus 1 b differentiated. So there's kind of 3 terms in the derivative. The first 2 terms can be put back together easily as a quasi-determinant. This term in the middle, if I use the little trick that a to the minus 1 differentiated is actually minus a to the minus 1 times a differentiated times a to the minus 1, I can rewrite it in this form here. So, but now let's take this a dash, that's your derivative of the a, and say it's got a particular form. So the form that you find in kind of Pfaffians and things is some sort of skew symmetric object. So if I make my aij the integral of these things here, an f of g minus gf, and then if I differentiate, I just get something very simple. So differentiating the a, an entry of the a, gives me an fi gj minus gi fj. So these f and g's are going to turn out to be just really simple exponentials. They're the eigenfunctions associated with the problem. And so I can turn here's my determinant. I can turn it back into here's my quasi-determinant differentiated. So I can turn it back into something that's really very simple. So it has a part that's got a derivative of the column. Then you don't want to differentiate the d part twice. So then you have a part where you've got derivative of the, sorry, this is the row here. And then this one here is the column differentiated, the next one. Then you've got two terms. And the two terms are sort of bilinear quasi-determinants. And they take the form, you can reformulate the fijj minus gifj into the columns and rows of the quasi-determinants, and you get this object here. So differentiating a quasi-determinant, if you've got this kind of skew symmetric entry, is a very simple thing to do. Okay, so we'll leave quasi-determinants for let's just shift to Pfaffians. So as I say, not everyone is so familiar with Pfaffians. Let's take a 2n by 2n skew symmetric matrix. Then if you work out its determinant, the determinant turns out to be a perfect square. And that thing that you square is your Pfaffian. So det A is a Pfaffian of A squared. So Pfaffian of A is basically just a polynomial in the matrix entries. And if you do this with a 2n by 2n matrix, you get a square of the determinant. If you do it with a 2n plus 1 times 2n plus 1, then you get 0, because the determinant of A for odd size matrices is 0. So the Pfaffian for odd size is 0, and for even size is it's non-zero. Nice way to write your Pfaffians, just to get a sort of feel for them. So we'll talk about skew symmetric matrices. So if you forget the bottom half of the matrix and write your Pfaffian as this nice triangle, you then get an expression. You can do an expansion like with a determinant. You get A12 times A32. So you basically expand about the first row, and that means taking out, there's no difference between rows and columns in a Pfaffian. So the first row is basically going across the top where you've got A12, A13, A14. The second row is you start above the A2, you come down, it's A12, turn a corner when you've got a gap, A23, A24. And so when you do the expansion, you expand about this entry and you cross out the row and the column it's in, or the two rows it's in, and then you're left with A34, and likewise, so you can get an expression using this triangular array for your Pfaffian. I'm going to lose lots of shorthand notation, and so my shorthand notation says that I'm just going to label basically the rows and the columns. So my shorthand notation says that if I say 1, 2, 3, 4, that is represents these four these entries here. So 1, 2 is just A 1, 2 from above. Okay, so we have Pfaffian identities, which are rather nice, and I'll just show you a couple of these, but then we're not really going to use these per se, because the non-commutative Pfaffian is a bit different. So the Pfaffian identities, if we have I'm just going to represent by a dot or a Pfaffian that's size 2n, and then the simplest identity is the following. So I won't say much about it. Basically says a Pfaffian with 2n entry, 2n columns multiplied by a Pfaffian with 4 more columns can be written as a combination, a bilinear combination of Pfaffians, each with 2 columns. Okay, so this is a typical identity. There are other identities as well. Okay. So one thing I do want to show you is looking at the inverse of a skew symmetric matrix. Now, because this is quite curious, and this is going to be sort of tie up to your quasi-Pfaffians. So if I take a matrix that's got entries ij, a skew symmetric matrix. Now, in terms of this notation, what I find is that, well, the inverse, not surprisingly, is also a skew symmetric matrix. And the entries can be written in terms of a ratio of Pfaffians. So this here is the whole Pfaffian. You might think this is a matrix we're taking here. Somehow, because the Pfaffian squared gives you the determinant, you might think that you get like squares of Pfaffians, but you don't. You get basically the ratio of Pfaffians. So you want the inverse of a skew symmetric matrix. You get the entries are Pfaffians divided by the Pfaffian, the whole thing. Okay. Right, so I want a non-commutative version of this. We could try various things. So if we take, say, a quasi-determinant of a skew symmetric matrix. So here's a nice skew symmetric matrix, and I'm assuming A12 is minus A21, and I try to say, oh, could this be a good candidate for a quasi-Pfaffian? Well, it's not. The problem here is that if I'm thinking about the commutative case, if I do this, I've got the inverse of, for this particular one, I've got the inverse of a odd size determinant sitting in here. Oh, sorry, the inverse of an odd size skew symmetric matrix, and that's determinant is 0, so you can't invert it. So this really doesn't work. So I can't use that. Well, you could say, well, what happens if I try something else and instead I take a bigger one? So this is a 4 by 4, but if I make this 5 by 5, then I've got something perfectly good for my inverse sitting here. But the outside rows are also making up a Pfaffian. So in the commuting case, this time I get that the 5 by 5 Pfaffian is vanishes. So this kind of approach won't give me anything, but you can actually do something if just a slightly more subtle approach. So we're going to take a quasi-Pfaffian that has this form. So you basically make sure your part of it is even in size, and then the last column and the last row are different from one another. Okay, and then if you do that, it's fine. So my notation is basically here, I'm boxing this alpha in the box represents the label in the last row, and the beta represents the label in the last column. If I do this, I actually get a nice candidate for a quasi-Pfaffian. Okay. So, in the commutative case, let's just have a quick look. In the commutative case, with this definition, I get the ratio of two Pfaffians, which, if I'm trying to match up my thing with known equations with Pfaffian solutions, the solutions are always ratios of Pfaffians, so they are things that look like this. So this is looking like a very good candidate. So I'm now thinking, well, we need to look at some Pfaffian equations and see if we can do something with them to convert them into non-commutative versions. So a system that I very much like is the Ota and Hirota coupled soliton equations. These are equations that have Pfaffian solutions. So this is in the commutative form. It's a system of three equations. And so with my definition of a Pfaffian, if I'm thinking about things being commutative, I could definitely take this and turn it into something that looks like a quasi-determinant solutions. So I'm going to take transformation. Typical transformation is that 2 is log of tau differentiated twice. In the commutative case, V is sigma over tau, and some V bar is sigma bar over tau. And my tau here is a quasi-determinant. Okay. Sorry, my tau is a normal Pfaffian. The sigma and sigma bar are Pfaffians with 2 extra rows in each. And the Pfaffians have the skew symmetric type of entries. So this is why I was talking about differentiating using these earlier. So the Pfaffians have skew symmetric entries. And I'm going to define, I'm going to define my entries. I'm going to have entries ij, which are coming from just like 1, 2, and then I've got entries that involve 1 and like C1 and 1 and D1 or D2, and these are defined just as derivatives of the F's and the G's. Right, so if I do that, they give me solutions. So the F's and the G's, so I've just written these out again. The F's and the G's are very simple linear relationships. So as you see in things like the KdV equation. So the relationships are just that if I differentiate with respect to xn, I get if I differentiate f1 with respect to xn, that's the same as differentiating n times with respect to x1. Okay, and the same for the g's, but there's a change in sign. The g's are usually sort of adjoint things to the f, so I get a change in sign when n is even. Okay. So I've got the sort of setup here, and these objects satisfy the equation. Now, I'm going to, so if we want to show that these are actually solutions, we differentiate the functions tau, sigma, and sigma bar. And what happens when you differentiate a Pfaffian, you end up with a Pfaffian with, oops, I don't quite know what people see at the other end, but this isn't fitting on my whole screen, so it's a little bit awkward. So differentiating with respect to a Pfaffian, we have that you get a Pfaffian with 2 extra columns, and they're the columns labeled by C0 and D0. I'm not going to go into the details of that, just believe me. And so I'm going to rewrite the system in terms of W because I don't want integrals in there. So I'm going to set U equals WX, and then my system looks like this here. So the W is now just one derivative with respect to X log, and the V and the V bar are the same. And so this is my system so I'm still thinking about commutative things, but this is my system with the W's. So I've got rid of the integrals just for convenience. Right. So I want to turn this into a quasi-Pfaffian thing. So let's do some differentiation for this particular example. So here's my Aij, and if I differentiate it, I get just this product that I showed you a bit earlier. And my I with C, I'm going to just say is given by GI, and my I with D is given by derivatives of my F. Right, so that's, we've kind of seen that, but I'm now thinking that I'm doing non-commutative stuff. Right, so here's my quasi-determinant differentiated, which we saw earlier down the bottom. So I'm going to just try and work out what happens in terms of this particular equation. So differentiating once with respect to X, if I differentiate the quasi-Pfaffian that has a border with derivatives, this DI means I've got I derivatives with respect to my thetas, and this means I've got the other border is S derivatives with respect to sorry, it's not R thetas, is it? It's F's and G's, sorry. So with my F's and G's. Okay, so this is what happens when I differentiate something. I'm going to use some very compact notation here. My notation is a little bit varied, I'm afraid, but so this is just notation where all I'm not worrying about the common rows and columns. I'm just worrying about different rows and columns. So I've got a sort of simple derivative here, and I'm just calling my quasi-determinants Q. Okay, so if I start doing more derivatives, what do I get? So this is one derivative. If I do 2 derivatives, every time I do a derivative, it gets a little bit more complicated because I have to differentiate, just thinking about one quasi-determinant. If I differentiate this first one at the top, I get a term from differentiating the lower border, the quasi-determinant, the last column, and then the part in the middle. So when I differentiate again, I get more and more terms. So we can see, say, differentiating with respect to X twice, I get something that's got quite a few terms in it, and they're all of different. So this is just a single term. This is a bilinear term, and then at the bottom I've got trilinear terms as well. So every time I differentiate, I'll get more complicated terms. So 3 derivatives, I'll get quadrilinear terms and so on. And I actually need 4 derivatives, I think. So I've got 5th order terms, but that doesn't matter. I haven't written out why. Why you can work out. It's very much like Hirota differentiation, what you get, and again, y. So you can work out all these different variables. So I'm going to choose my W to be, which is my solution to the equation. I'm going to take it as the quasi-determinant with, I'm now moving to thetas. These should really be I had F's and G's before, so the thetas are like the F's and the G's. So the thetas are the F's, the theta transpose are the G's. Okay, so apologies for switching things. And my V is basically the quasi-determinant with a row of F's and a row of F's with, or thetas with transpose, a column thetas transpose, and the V bar just has, is a quasi-determinant where the borders are the G's or the G's. Okay. So basically substitute everything in the equation and, oops, I get the following. Now I'm going to set Q with borders with just two F's in the borders equal to 0, and the Q with two G's in the borders equal to 0. And what I get is, and I've put it in a different color, I get a non-commutative version of the equation. So the whole system, in fact. So the system, the stuff in black is the original system, and the blue is the extra terms. So the kind of thing we get are not too outrageous. They're basically commutators of, this is the W differentiated with respect to X and W differentiated with respect to Y. So that clearly in the commutative case will vanish. We also have terms with, or it's a term in the second equation that has a V commutator commutated with W differentiated twice with respect to X. So again, that clearly vanishes. And in fact, all the terms clearly vanish. So in the second equation, there's also a WX commutated with V. So if we go back to the commutative version, we get exactly what you'd expect. Okay, so that's my non-commutative Hirota equation. Now, I've sort of skated over one or two features here, and this is, it's not guaranteed that these Q's vanish. So these two, where I've got similar things in the borders, they clearly vanish for the commutative case, because that would be involve a Pfaffian that's of odd size sitting there, so they clearly vanish. But it's not so clear they vanish otherwise. It could be that if I do some condition, some simple condition on the quasi-Pfaffian, some simple constraint, they really do vanish. But this is something I need to think a little more about. So if I say, oh, well, I don't know whether these vanish, and I put them back in again, I get something much more interesting. So I'm going to call the two that I expect to vanish, I call them J and H. And what do we get? Well, we get a very complicated looking thing. So our first equation has the basic stuff along the first row, has the usual, the commutative stuff, and then it has all these extra terms. Now I've done this using computer algebra, so if I use all these fields, they do actually vanish, but they're derivatives of the fields in here. So the first equation has all these things. It has this extra J and this extra H. And it's not, I could tidy this up a little bit more, but it's not clear exactly what is going on here. We'll look at the second equation as well. The second equation is in basically the one in V. And again, this has lots of terms in it. And it looks something like this. But again, it really is satisfied putting these terms in. The third equation is just the sort of V-bar version of this, which mirrors this. So I haven't written it down. So the problem here is that we definitely have quasi-determinants, quasi-Pfaffians, and derivatives of quasi-Pfaffians that you can put together into an equation, or several equations. The problem is this system has maybe too many equations or too many variables for to be kind of certain exactly what's going on. There are actually, in reality, more variables here. There's a W bar variable which has an equation, and well, you're seeing the W bar here. In fact, there's a W bar equation itself, so there's 3 equations plus a W bar equation. There's 2 other equations with things like the V, so that's 6 equations, and then there are actually an equation relating all these bits and pieces together. So I think there might even be yet another equation. So I think there are probably the same number of equations as variables, which is a sort of good thing, but it's quite a strange system. But it may be that I can sort of collect these things together in a way that is easier to interpret. So maybe my choice of quasi-Pfaffian here, I could collect sort of combinations together to give something simpler. So anyway, this is the sort of full non-commutative version. Right. Okay, I want to quickly look at a couple of other systems. We've got the sort of systems that have not been looked at by so many people. So 2+1 Sine-Gordon system, or the Konoplyanka-Rogers system, is a Pfaffian equation. This is quite a simple system, and this has similar sort of things. It's got a U. This one is got some complex stuff in it, so it's got a U, which is a log of a tau. So again, you've got ratios of Pfaffians. Tau's a Pfaffian. Tau bar is a Pfaffian, and again, we've got ratios of these things here. And V, this is not a ratio for the V, but when you use the V, you are taking derivative. You've always got a derivative of the V, so you'll always get sort of ratios of Pfaffians. So this is another one that you can put into quasi-determinant form, certainly. And so the solution is just a Pfaffian, and again, I've labeled it here. And this time I'm going to stick totally with thetas. So this is an interesting equation because it has the x and the y variables are the same weight to one another. So if I differentiate my, if I've got an entry in the Pfaffian, this is my entry in the Pfaffian, just labeled by theta I, theta j. My thetas are eigen functions. If I differentiate with respect to x, I get this kind of thing that we've already seen, but this is now, instead of having like an f and a g, you've just got thetas. So with derivatives, so I've got a differentiating with respect to x, I get a theta times theta differentiating with respect to x, and then a theta x times theta of i's and j's. So this is my entry. But if I differentiate with respect to y, because it's the same sort of weight as x, I again get some expression with y's in it. But notice here that the derivative with respect to y gives something different because there's a kind of change of sign over the derivative with respect to x. And again, my sort of what are going to be by border terms are just derivatives of these thetas. Okay. Right. There's another equation, another Koff-Veseloff equation. This one is also got Pfaffian solutions, and it has the same kind of structure as the Konopchenko-Rogers system. So again, it has this structure of differentiating with respect to entries with respect to x gives something very simple, and with respect to y gives something simple but different. So they're all candidates that you can differentiate and turn into quasi-Pfaffians, at least in the commutative case. So the thetas in this one obey simple relationship where you've got theta t is given by minus 3 derivatives with respect to x, minus 3 derivatives with respect to y. So all these thetas in their simplest form, they're just going to be a sum of exponentials with things like kx plus py plus something k cubed t plus p cubed y, something like that. So they're going to be sort of simple exponentials. And then finally, I want to show you the BKP equation, because this has the same structure again. And so again, in theory, one can turn it into quasi-Pfaffians to commutative without any trouble. So this one is a fifth order equation, and we have in here the x is a weight 1 variable, so it just has this. The y here isn't the same as the other two I showed you. The y is a weight 3 variable and the t is a weight 5 variable. So you have relationships between your thetas that take the form of things like 1 derivative with respect to y of a theta is 3 derivatives with respect to x. 1 derivative with respect to t is like 5 derivatives with respect to x. Now, I've not written an awful lot more down. So now I'm going to show you some, this is, again, don't get lost in the notation, but so we basically, with these equations, we have various kinds of quasi-Pfaffians that we want to use. So the quasi-Pfaffians here are, if I write down with lots of thetas, this means, by the way, down the leading diagonal, I put zeros, but I think I'm actually going to probably need to have a theta 1 term, but we'll not worry about that here. Okay, so this Pfaffian, this quasi-Pfaffian has columns that have integrals in them. So just looking at the entries, so the last column has the integrals in it, and the last row has the integrals in it as well. But the point is that the theta here is a theta b, and the theta here is a theta a. So they're different from one another, and that gives you the structure of the quasi-Pfaffian. I'm going to have some quasi-Pfaffians that just have simple thetas. So some are going to have thetas in the last column and thetas in the last row and derivatives of thetas. And so they're going to be labeled with, basically, if I put a d with a theta, I get a dn means an nth derivative with respect to theta, and a cn is an nth derivative with respect to theta transpose. Okay, so just a quick flip through the different notation. So this one here has a C0, so that's basically saying I take my last column and I just have thetas in it. The second one here has a D0 theta, and that basically means make the last row thetas and the rest are the integrals. And then you also have ones where you have, so this is with derivatives as well. Let's go through those. And then you finally have ones where you've got a last column which is thetas, and a last row, which is thetas and derivatives of it, and that's described by boxing. I put a drcs in the box, and that means this is s derivatives in the last column and r derivatives in the last row. So I'm going to have all these different objects, and they're going to give me my quasi-Pfaffians. So if I differentiate, say, this quasi-Pfaffian here, the one with the integrals in the last row and the last column, I actually get something very simple. I can reabsorb. When we did this earlier, we had like two linear terms and then these two bilinear terms. I can absorb the linear terms, get absorbed back into the expression. So I just get two bilinear terms coming out of this differentiation. And so I get these Q here. If I differentiate the ones where I've just got thetas in the rows and the columns, I get something slightly different. Now, so what can I do with these? Well, the aim is the following. I'm going to choose an appropriate psi. Psi is actually, I don't think I showed you this. Psi is the sort of linear problem. This is for the Novikov-Veselov at least. The linear problem looks like this. It's just a psi xy plus u psi equals 0. So I'm going to choose psi, an appropriate eigen quasi-Pfaffian, u, an appropriate quasi-Pfaffian, v, an appropriate quasi-Pfaffian, and also the Novikov-Veselov had this capital theta in it, which was related to u and v. I need to choose these so that the Novikov-Veselov equation is satisfied. Now, I know I can do it if I let everything commute, because I can write all the terms down in ratios of determinants that can be written as quasi-Pfaffians. So I know that will work. Question is, what happens if you don't have things commuting? Well, this I have no more. I haven't written the result down on the slide, but I've got my student Chen Xu is looking at calculating some of these things. I have the calculation for this in the basic form, and you get it, if you calculate psi xy, because when you differentiate it sort of proliferates terms, you get quite a lot of stuff in here. So calculating psi xy, you see that you actually have to have in your linear problem, I think, is going to have to be more complicated, because I think it's going to have a psi x term with some coefficient and a psi y term with some coefficient, as well as the u times the psi term. So I have got it here, but I can't show you exactly what you get. So it's kind of work in progress. As I say, I know how to write these things down if things are commutative. So it's a case of what exactly do you get if it's not commutative. And the thing is, because when you differentiate your quasi-Pfaffian, you always get quasi-Pfaffian. So you can cast everything in a form of quasi-Pfaffians, and hopefully, like the case for the Hirota-Ota case, you can again piece things together and come up with some equations. I haven't got the equations, as I say. I have calculations for just looking at this part of the linear problem, but I don't have the calculations done for the Novikov-Veselov and these other equations. But they shouldn't be too difficult to do. Okay, so I'm going to essentially stop there and just give you a bit of just conclude. So I've got quasi-Pfaffian. It's a very nice definition of a quasi-Pfaffian because it works like the ratio of Pfaffians in the commutative case. As I said, there are other possible definitions. There are some technical difficulties as well that I haven't exactly skated over, but the quasi-Pfaffian, to get everything ordered correctly, rather than having, you know, in a normal Pfaffian, you would have, you'd be using a skew symmetric matrix. Well, for the quasi-Pfaffian, you really need to get everything ordered correctly. You need to have a, you need to take the transpose. What goes in the bottom part of your matrix is the transpose of all the terms in the top half. Otherwise, the order of the thetas doesn't really work. But that's not, I don't think that's a big problem. So there are, like, the same as quasi-determinants. The quasi-Pfaffian is basically a quasi-determinant. You have identities. There exist quasi-Pfaffian identities as well, like the determinant identities. I don't think I particularly showed you them today. Differentiation of the quasi-Pfaffian gives you something simple. That's the key to it. For the Hirota-Ota system, we cast the solutions as quasi-Pfaffians. It's a little bit unclear why the final system is so complicated, but it exists that you can actually put this stuff together. So yeah, you can write these equations in terms of quasi-Pfaffians and their derivatives. So you can actually put stuff together. Still got to really try this out for the Novikov-Veselov and the 2+1 Sine-Gordon, and also the BKP. The BKP might actually be, although there's high derivatives in the BKP, it might actually be a bit easier. Okay, I think I better stop there, right?
Okay, thank you very much for exciting talk.